Okay, numbers are plateauing that have joined up. So welcome to another session of the round one training. Um, this sounds like it's sort of a very active session. It is from Andy French, but of course, if you're going to benefit from it, it's no good sitting and listening and watching. You've got to do it yourselves. So this is just how you might go about solving a problem where you could get stuck. And there's nothing wrong with getting stuck. I'm always getting stuck. But you've got to sort of get that paper out and write things down and try it out. If you don't try it out, you'll gain no benefit from watching. This is merely the sort of enthusiasm and techniques for getting going with these problems, but do it yourself. So do have a go. Okay, well, there we are. That's enough intro for that. So let's get on with the session. And
Right.
Dr. French.
Thank you very much indeed, everybody. Good evening. Good evening. We are at session number 5. We've got a few weeks now, a little bit of half term, and then we've got round 1. Right. So we're coming to the end. I think this is going to be the last session looking at the 2022 paper. So I'm going to pick, I'll kind of run out of the sort of low-hanging fruit, if you can even call it that. So we're going to do some slightly tougher problems. And I think as Professor Hughes was talking about earlier, I think I'm going to try and indicate the kind of key ideas, how you can make some traction. So we're going to have a little look at some classical mechanics, a really lovely problem on a bowl, which we'll start with. We're going to also do some optics as well, and we're going to look at some capacitors. And I think the beast problem of the paper is problem U. So if you've had a go at this, you'll know what I mean. Anyway, maybe one of you can find a very snazzy way of getting it out very quickly. But I'm going to show you the slow, steady, but it is a bit of an adventure. So we get to U, hold on to your hats, and this will be really a good way to round off this paper. We'll probably go to 2019 next time. So we'll put some links in the chat before the end about how to access those papers. But yes, if you go into the usual place, download the one question per page for 2019, and we'll be starting that next time as a sort of warm up for BPhO Round 1. Okay, so let's go for problem L first, which hopefully you've had a go at this one, and if not, maybe we can have a look at it now. So here we go. Right, so what we've got, this is the sort of thing that might be in David Morin's book. If you've not heard of this, it's going to be, I think it's the Introduction to Classical Mechanics, yeah, something like that. Where is it now? It's a big red book, basically. Okay, it's one of the most beautiful books around. And basically, it's filled with probably thousands of these very simple, elegant looking problems, but actually turn out to be quite interesting and often very, very tough to actually solve, but beautifully stated. So if you like that kind of thing, some of my students in the past got so obsessed by this that we had a Morin Fest at Christmas. David Morin is also renowned for writing very, very quite amusing limericks relating to physics ideas. So the idea from this Morin Fest, perhaps you could do it too. Everyone had to wear Christmas attire, write a physics-based limerick, and then solve their favourite Morin problem. So yeah, that's something you can get have a go at. So this is a Morin problem, homage to David Morin. So what do we got? We've got a thin rod. All right, it's in a smooth hemispherical bowl, which you can see here, and it's both touching the interior and the rim, as shown in the figure. All right. And the rim remains horizontal. Okay, so that's the bowl is kind of fixed. The bowl's not going to move. It's all about the rod, right? So we've got to try and figure out the radius of this bowl in terms of the length rod and the angle theta. So what we want, our goal, is to find R as a function of L and theta. All right, and I'm gonna skip to the actual answer to this, because some of you might have had a go at this one, and it's rather nice. The actual answer is R is a fourth of the length times cos theta over cos 2 theta, which is rather pretty. All right, so I don't know about you, but I kind of get a sort of sense of when maths appears rather elegant. That's that sort of a way into the beautiful universe. All right, so and I think there's a long history of this. So Paul Dirac, the great physicist who discovered the Dirac equation and antimatter, predicted antimatter, I think was also driven by a form of aesthetics as well. So we don't have to be just driven by sort of practical problems to solve. Right, so let's have a go at this. How might we start about this one? Well, this is a statics problem, so we're going to look at some forces, and we're also going to look at geometry. All right, so the first thing I would do is label some forces on this rim. Now, we've got 2 points of contact. So we're going to have a normal contact force, sort of perpendicular to the line here. And I'm going to call that something. I'm going to call that R2. And so that will be, and also I want to try and use some geometry here. So if I have angle theta is also going to be this one, all right? Because we're going to be resolving forces. Now, what's a really good coordinate system? Well, probably one which is parallel to the stick. All right, there's other things you could choose. All right, so there's my coordinate system there. What else can I do? Right, let's call that point B. All right, and let's call this point A here. Right, what else have we got? Well, we've got some forces acting at this point. Now, because it's a hemisphere, where will, put this into the chat, please, where will the contact force at A, the normal contact, act? In fact, it's the contact force because it is a smooth hemispherical bowl. Okay, so where must the force act at point A? What have you got, Nina?
We're getting 90 degrees, normal to the surface, vertical.
Yeah. Right. Okay. Well, there's we can do even better than that. It's 90 degrees because it's a circle. That's actually going to act towards the center of the circle. All right. So if this was any old shape, all right, this might be complicated. But because it's a circle, a section, because it's a hemispherical bowl, all right, we know that normal contact force would act towards the center of the circle. Because if you think about it, that's it's on a radial. Let's call that R1, shall we? So these are normal contact forces. So we can call normal contact forces R1 and R2. Obviously, the magnitude of those are what's written. These are vectors. Right, now it's smooth, so that means there's no friction, so there's no tangential component. All right, so we just write that down. Now remember, if you're new to today, I mean, I would always recommend writing all over your papers for your assumptions, but I'm kind of describing my thinking with the words here. So I'm deliberately solving these problems pretty slowly. All right, but this is as I'm thinking through something, the things that I can figure out, I'm writing down. So no tangential force, all right, because it's smooth, there's no friction. Okay, what else we got? Well, we can also have a little look at the angles of this. So from geometry, if you think about it, this angle here must also be theta, and this angle here must also be theta. Right, let's make that a little bit bigger so we can see that. Right, what else we got? So we also want the center of mass of my rod, which is about there. Okay, so that's going to be a force, and that's the weight that's acting. Let's call that mg. And so we need to invent something here. We've got some strength of gravity. Notice that does not appear in the answer, but we're going to need to use it if we're going to balance forces, and hopefully it will cancel somewhere. And so we've got, let's just say that the rod of mass m. All right. Okay. Is there anything else we've got? Well, also, if you think about it, think of our coordinate system, we're going to have to resolve the force of the weight as well. All right. So if that's 90 degrees, well, let's just have a little look at our angles here. So that angle is theta. Then this angle here is 90 minus theta. So this angle here must also be theta. All right. So I'll put in the margin in my sort of in my blue pen what my kind of ideas are. I'm going to resolve forces. Okay, so I need a coordinate system to make sense of that. And also, I'm going to consider geometry. All right, so there we go. There we are. And also, if we think about the sort of where these forces are acting, we might also draw this as well. So here's our, this is sort of, that's going to be our radius here. So our angles, if you think about it, form an isosceles triangle of where those points act. So that's going to be A, and that's going to be B. All right. Okay, so that might be useful. So I'm writing down what I think is going to be handy here. And another thing I might want to do is I want to sort of work out what that length is. So that length there, all right, from the center of mass of my rod is going to be L over 2. Okay. Right. So there we go. Right. So I think that's pretty much everything we need. So what we can do now is we've got kind of two things we want to apply because it's a static situation. So yeah, this is not an energy thing. It's not a before and after. It's not a momentum thing. There's no conservation law. So we've got kind of two possible rules of physics that we can apply. What are those two rules that we can apply to a static situation?
Yeah, resolving forces and moments, net torque is 0.
Brilliant. Right. So excellent. So statics problems mean we've got two options here. So let's because this may not seem obvious at the moment. So I'm going to do Newton 2 and I'm going to resolve and I'll think about resolving moments. All right, because sometimes you might get an expression which is really simple and other times you may not. So let's just pretend that I don't know what the answer is and I'll work it through. So let's do Newton 2 and we'll do parallel to the rod. So that's, in this case, it's the x direction. So Newton 2, mass times acceleration is vector sum of force. In this case, the vector sum of force is 0. We've got x going positive, so from like A to B. So what do we got? We've got R1 cos theta, which is the components of the normal contact force at A. I suppose I could use RA and RB. All right, let's go for this one. Okay, and then I've got R2 sine theta. Sorry, no, I haven't. We've got mg sine theta act in the opposite direction. All right, so the normal contact force at B, that's going to be perpendicular. That's in the y direction purely. All right, so in that case, immediately we can figure out what R1 is in terms of angles. So that's going to be mg sine theta over cos theta or mg tan theta. Fantastic. All right, so if we know the weight, we know the angle, we can find out the contact force at 1. Brilliant. Right, okay, so let's work out the other one. So Newton 2, parallel to the y direction. Y direction. So what do we got? Well, that's also going to be 0 mass times acceleration. So what have we got? We've got R1 sine theta. Whoops. R1 sine theta. Okay, at A, we've got R2. And then we've got a component of my weight, which is acting downwards. So that's going to be minus mg cos theta. Oh dear, my page is going a bit strange today. Mg cos theta. There we go. Hope that's all right. And if anyone is new and thinking, what is this resolving forces I'm doing here? Well, just do one of them so you can see what's going on. So mg, there's my weight. Here's my sort of y direction. So there we are. That's y and that's x. And if that angle is theta, I can decompose my weight to a force in the y direction, which is mg cos theta, because that's a right angle triangle. And I've got in the other direction, let's go for blue here. I can do a vector sum of the green and the blue arrows. That's going to be mg sine theta. All right. So that's what I mean by my resolving forces. Okay. So that's a very, very useful tool and to be able to do kind of just by writing it down. So the effort you need to put in is making sure we've got Newton 2, mass times acceleration, mass times ac, and this is the vector sum of force. All right. Don't try and simplify it straight away. Just make sure you've written down all the components. If you miss one out, you're kind of stuffed, basically, because this is the starting position. Right, so what does that tell me? Well, therefore, let's figure it out. So we've got R2 is equal to mg cos theta. All right, and then minus R1. We've got R1, so that's mg tan theta sine theta. All right, so that's going to be R1. Okay, all right. Well, that's looking a bit more complicated. All right, that doesn't simplify particularly nicely, but that might be useful. Right, what else could we use? Well, let's go for moments. Now, we've got some options here. We can do moments about A, or we can do moments about B. Now, I guess you could do either here, to be honest, but R2 looks the more complicated expression. So I think I'm going to take moments about B. So since R2 is more complicated, and R1, take moments about B. Okay, because remember, what am I trying to do? I'm trying to find an expression for R here. All right. And there we go. So I might need to do some geometry here, or perhaps it might just even allow me to do it. All right. So let's go and have a little look. And let's firstly just do a little bit of geometry. So I'm going to go and hopefully you can see this, but I'm going to redraw my part of my bowl here just so I can sort of see what's happening. So here's my bowl. There we are. Hope that's not too bad. A little circle. We've got our rod here coming out, and there's my center of my hemisphere. So there we go. So don't feel like you have to stick with the original diagram. We've done it. It served us quite well for forces. Maybe we need something else as well. So that's my angle theta. Remember, I know that from before. All right, and there's angle theta here as well. All right, so this is this diagram that we drew first. That's splitting in two. So let's call that something. Let's call that distance L, and that whole distance, so this one here, is what have we got that one? So that's sort of that's going to be our length minus L. All right, something like that. And from geometry alone, hopefully you can see that L, that distance there, is going to be 2r cos theta. All right. All right. So what we're trying to do is we're trying to write down all the relationships we know and see if we can then combine these. All right. So we've got the forces, which is quite nice, but we kind of want those all to cancel. All right. We want a geometric relationship. All right. So let's give this a go. So what we can do, if we take moments about B, remember, because point B here, this one, as the less complicated version of contact force R. So what do we got? Well, if we take moments, we can take moments about any point we like in equilibrium. And so let's go about B. So what I'm going to do, let's use a green pen for this one. So if I go for clockwise moments, all right, about B. All right, so what have I got? Well, I know that's going to be 0. There is no net torque. So if I just remind myself of my forces from my diagram, if we have a little look at this one here, so we've got sort of R1 sine theta, that's the sort of perpendicular component to the length of the rod, multiplied by L. All right. So, and if I'm going, that's going to be going, which way around am I going to go? So that one, well, yes, if I go for this way around, so that's going to be going this one here. So R1 sine theta. Okay, that's about B. That's it. This is about B times L. All right. What about the weight? Well, that's going to be going the other way. So mg cos theta, and that's going to be times, well, the distance between the center and the other part. All right. So what have we got? We've got this distance here is what we want. So what have we got? We've got so L times, oops, we've got mg cos theta. So that's going to go the other way. So mg cos theta is a component of my force. And I want the distance between where my center of mass is to my little rim here. All right, so let's figure this one out. So if L on 2 is this part here, we're going to be taking away R from that. So what we'll do is we'll say, okay, that's going to be multiplied by L minus L on 2. Okay, so I think that is right. Let's just have a little look at that one. Do I mean that? Is that correct? Yeah, that's all right. So if you think about where the center of mass is acting, yeah, so L, of course, is the length of my rod. So if we just, I don't know if that's clear here, but if I was to have my center of mass here, that's where my weight's acting. There's mg. Right, that distance there is the length of the rod over 2. All right. So if L minus L on 2 is going to be this little distance here. Okay. So I find when I'm doing moments calculations, I'll often need to redraw something at least twice so I can sort of get the geometry, get the distances. All right. So remember, perpendicular force times the distance. And I think that's all sorted. So what does that mean? Well, let's have a look what we can do there. So that will give us another expression for R1. Okay, so let's do that. So what we got? We've got the L's. No, the L's don't cancel. So we've got R1 sine theta L equals mg cos theta L minus L over 2. Okay, and if we then divide that by L and sine theta, just check my notes if that's a good thing to do. I think what I might do, I think I might expand that out first, actually. Let's have a little look. Yep, let's do that. So, or probably what would be a good idea, let's just use mg tan theta for R1. So what do we got? We've got mg tan theta, and we've got a sine theta here, and an L. That's mg cos theta, L minus L on 2 mg cos theta. Right, now we've got to sort all this out. So what have we got? We've got, here we go, a little relationship. So we've got, where's our R here? Oh yeah, there we are. We also might want to use L is 2r cos theta, because the length of the distance between A and B doesn't matter. So if I just highlight what I've done there, so R1 is mg tan theta. Now let's substitute for L. So we have L is 2r cos theta. So we've got mg tan theta. I'll make this nice and big. Sine theta. I'll use a different color for this one. 2r cos theta. All right, and that's equal to mg cos theta. And we'll have our L as 2r cos theta. Let's give that the green one. All right, and then we've got our last bit minus L on 2 mg cos theta. Right, let's just sort all this mess out. Okay, so we want R on one side. Let's see what else we've got. So let's put R. So we can cancel out the M's first and the MGs. Let's get rid of all of those. MGs and an MG. Let's have anything else that cancels. We've got a cos theta, which we can get rid of as well. At least one of them. Cos theta, and cos theta. Hopefully I've got the right expression here. We'll soon find out. And I think what we can do is we can divide everything by 2 as well. Let's just keep the 2r there. So what have I got? I've got 2r. Let's factor this all out. We've got a tan theta and a sine theta. We've got a 2r cos theta on the other side, so minus cos theta here. And that equals, well, I've got the minus sign wrong. Let's keep that there. Minus L on 2, and that is it, I think. So therefore, what have I got here? Oh dear, have I got this one? No, that's I think that's okay. So I've got, let's just multiply these out. So we've got R is going to be L on 4, which I think if you look at the answer, that is L on 4. That's looking good. And then we've got a 1 over cos theta minus, well, let's call that sine theta over sine theta times sine theta squared over cos theta. So I'm using tan theta is sine theta over cos theta. So this is becoming a bit of a trig fest. All right. Okay. And we're nearly there. So L on 4. So if we multiply cos theta here by cos theta over cos theta, we've got 1 over cos theta squared minus sine squared theta. That's all over cos theta. All right, let's keep going. So L on 4, we've got cos theta on top. And the difference of cos theta is, of course, the double angle formula, which is cos 2 theta. So there we go. Hurrah. So a bit of a trig fest. But hopefully that might sort of give you some tips of how we did it. So in recap, firstly, I would draw our diagram. I'd add the forces on. So that's my bullet point, resolve forces. I'd use a sensible coordinate system. You could choose horizontal and vertical, but it kind of makes sense to use the geometry of the problem, the symmetry of the problem. So we're going to use the length of the rod as my x direction. I then Newton 2. We might get something useful, all right? But obviously we've worked out things that we don't really care about, R1 and R2. R2 was more complicated looking. So if I'm going to do moments, I don't want an expression involving that, probably. So I've decided to take moments about point B because R2 doesn't have any moment about itself. all right, about point B. There is no distance multiplied by the perpendicular force. So I do my moments, and moments I always think I have to be careful about because of the geometry of the situation. So I've redrawn the figure. All right, so I've called L being the length of the rod between A and B. Okay, and then I've got, from my geometry, I can work out what that is in terms of R, the radius of my hemisphere. And there we go. Hope that's all right. And there we go. We get a bit of trigonometry to just have to sort of persevere with this one. So even though I made a mistake here, I put a minus sign wrong here. But that's okay. That's all right. That sorts itself out. You know, this isn't a mistake. It's just a bit inelegant. All right. Okay. Anyone got any questions? I hope I'm still broadcasting. Are we all good?
Yeah, you are still broadcasting.
Excellent.
Yeah,
Right.
we're going through the questions.
Sorry, say again?
All good. We're going through the questions.
Fantastic. Great. We've got the super keen. Right. So T, we're going to do some optics now, I think. All right. I don't think we've done any optics yet, actually. I've avoided that. There we go. Right. So what have we got here? Glass prism. So here we are. Let me just bring my notes up so I just check there's no gotchas for this one. So what do we got? We've got a glass prism here, and we're looking for the range of angles that light will emerge that is incident on face AB that emerge from face AC. So this is a refraction problem. And so just like basically how computer graphics works, we need to do some ray tracing. So again, there's a lot of geometry here. So we want something that's incident on the face AB. So let's just have an angle, shall we? So firstly, the key thing for these is to always draw your normals. So let's have one here, and let's have a ray which is somehow incident to this. Let's call that angle θ1. All right, and just to remind ourselves, this is air, and this is also air, and this is glass. And the refractive index of 1.4. That's what we read. That's the ratio of the speed of light in air divided by the speed of light. Excuse me, in our glass. So the speed of light, the average speed of light, will sort of slow down by a factor of 1.4 as it enters our glass. Right, so we want to draw some geometry here. So what's going to happen? Well, it's going to refract. It's going to bend towards the normal, because that's what happens when we go into a medium of greater refractive index. So we're going to get a light here. Of course, it's going to be a straight line because the speed of light hasn't changed inside our glass. And then we're going to draw our normals again. I think I'll change color for that. And then we're going to bend away from the normal. All right, so we're going to sort of have it something like this. Okay, so let's call that angle θ4 here. Let's call that angle here θ2. And there's a little angle here. All right, if I just do that one, we'll call that angle θ3. Okay, so we need all the angles to sort of chase our thing through. And let's go and have a few other angles as well, because we're doing some geometry here. Let's call that alpha. Let's call that beta. All right. And the refractive index is n. Okay, so we've got all the possible angles that we might want to find. We know that alpha and θ2 must add up to 90 degrees. So does beta and θ3, etc. And then we can use Snell's law to relate all those things. So let's just write down what we know. Okay, so which I think is a general principle for pretty much all these problems. Let's do our normals first. What do we know? Well, we know 90 degrees is equal to alpha plus θ2. Let's call that equation 1. We also know 90 degrees is going to be beta plus θ3. Let's call that equation 2. What else do we know? So we also might find that we've also got a triangle as well. So I'm going to sort of put that here. So we know that's 75 degrees. So this is basically geometry first. Because essentially, if we look at a physics problem, it's really a mathematical problem, and we're applying the law of conservation of information, if that is a thing. So the number of unknowns must equal the number of equations which are independent. So if you're ever kind of stuck, I remember at university being stuck on things like thermodynamics questions. I think, how do I proceed here? Well, the idea is just to write down things that you know in an algebraic way, a nice clear way, and then you can try and do some mathematical problem solving to try and eliminate things. But the physics idea is to sort of say, well, what does that actually mean? you know, from a physical perspective. But if we haven't got the maths in front of us, that's kind of hard to understand, I think. So there we go. So if we got alpha, beta, and not 75 degrees, hopefully you can see that that must add up to 180 because it's a triangle. Okay, plus beta plus 75. Let's call that equation 3. What else can we know? Well, we can do Snell's law. Super quick. What's Snell's law for theta 1 and theta 2?
Nice. Yeah, we got n1 times sine 1 equals n2 times sine 2.
Okay, so and remember in this case, air, our refractive index is 1. So what I'd write for Snell's law, I know it sounds obvious, but I'd write 1 times sine theta 1, right, equals n. So n is our refractive index of the glass, right, times sine theta 2. I know that 1 times sine theta 1 is sine theta 1, but that's the kind of thing, it's very easy to get this the wrong way around. So your statement of Snell's law is what I'm writing down. Then we can rearrange it later if we need to. So similarly, 1 times sine theta 4 is going to be n sine theta 3. Let's call that equations 4 and 5. And I think that's pretty much everything now. So let's just go back to our question. What do we want? So what range of incident angles will result light from the air that's incident on face AB will emerge from face AC. So what we're really looking there is that sort of we want a condition on theta 1 given a range of theta 4. Okay, so basically theta 4, well, what's this going to be? All right, so let's have an expression for theta 4 in terms of theta 1. So that's really what this is asking for here. So i.e. a goal. So we kind of stated the goal in the previous question. So we want theta 4 as a function of theta 1. Okay, that's what we want. Okay, so let's give this a go. So right, what we need to do first, we need to eliminate our alphas and betas. So if we combine 1 and 2, equation 3, then it gives us an equation for theta 2 and theta 3. All right, so let's give that a go. So if we do 1 plus 2, what have we got? We've got 180 is alpha plus beta plus theta 2 plus theta 3. And we know that 180 is equal to alpha plus beta plus 75 degrees. All right, so therefore, we can just sort of look at this bit here. All right, so they must equal each other. So therefore, we could subtract one from the other if you like, but what we've got, theta 2 plus theta 3 is equal to 70 degrees. All right, so all right, and therefore, theta 3 is 75 minus theta 2. Right, now let's look at our Snell expression. So what we want is theta 4 in terms of the others. So let's give this a go. So theta 3, so let's have this. So theta sine, so in 5, we've got sine theta 4 is n sine theta 3. Now theta 3 is 75 degrees minus theta 2. And theta 2 from 4 is related to sine theta 1. So theta 2 is going to be the inverse sine of sine theta 1 over n. Okay, so we're getting it with a slightly inelegant expression, but that's okay. It's good enough. So if we replace theta 2, therefore we've got theta 4 inverse sine of n sine 75 degrees minus theta 2, which is inverse sine of sine theta 1 over n. Yuck. All right. All right. So we've got an expression. Now, how can we make some use of this? All right. But in principle, we could plot this versus theta 1, and we could see what we could find. We could use this to model our output angle given our input angle. But now we need to sort of think about what we want. So let's look at the sort of various options here. So what's the domain of our inputs? So 0 theta 1 is going to go to 90 degrees. All right. So, you know, any angle is possible from along, well, not inside the prism, obviously, but from sort of along BA to the normal, that specifies the range of our inputs. So now we know, all right, so since n equals 1.4, therefore sine theta over n must be less than 1. All right. So therefore, we can expect that basically merged for all angles of incidence, right? So what we've got is that there's no limit on what sine theta to the minus 1 of that is, because the argument of sine to the minus 1 is less than 1. All right. So and if you think, hang on a minute, is this true? All right. So think of our sine function of theta, right, between 1 and minus 1. Okay. So we're looking for sine theta 1 is less than 1 over n. Okay, so this is sine theta. Yeah, there's going to be some angles for this that work. All right, we're not asking for sine theta is bigger than 1, where there'll be no solutions. So there we go. So we get rays to emerge for all angles of incidence. It's never going to be a sort of total internal refraction, a total internal reflection kind of situation. So what we'd like is well, what's the largest theta for? Okay. What's the largest theta for is going to be? Well, that's going to be when sine theta 1 is going to be 1. All right, so it's going to be the smallest thing we're going to take away from 75 degrees. So let's work that out. So because remember, for this situation here, when we're taking away a positive thing, this is always positive, right? So always greater than 0. So the smallest angle we've got is going to be the largest value of the thing in there that I've just put a bracket around. So what's that going to be? Well, when sine theta 1 is 1. So theta 1 is 90 degrees. So when theta 1 is 90 degrees, it's literally going along A to B. Okay, you might say, well, hang on a minute. Is there any actual light that's going into my prism? So it'd be very, very faint. But there we go. You can imagine a sort of micro radian from that. When sine theta 1 is equal to 1, that means that theta 1 is 90 degrees. All right, what have we got? That means we've got sine to the minus 1 of sine theta n is going to be sine to the minus 1 of 1 over 1.4, which is 45 degrees. That's, of course, that's the critical angle for total internal reflection as well. All right, which is very nice. Okay, so if we then stick that in, therefore theta 4 max is going to be the inverse sine of 1.4 times sine of 75 degrees minus 45.6 degrees. And if you pop that into your calculator, you'll also get, well, some slightly smaller, 43.40s. Okay, so there we go. There we are. So there we go. That's what that was. Now, you might also ask the question: is that what range of theta 1 gives you a real value of theta 4? Okay, so what you might find, if that's the sort of smallest quantity, we want basically the argument of our inverse sine function to be less than 1. Okay, so because we've got theta 1 is 90 degrees, but can any angle work? You know, if we had theta 1 being 0, all right, so would that work? Well, you might find that also the thing in the brackets is that this inverse sine is going to be fine, but we might have an inverse sine of something which is which is bigger than 1, so that's not allowed. So let's try that again. Before I do that, has anyone got any questions? Because I want to sort of go down to the last bit before I answer any. So do we have any questions about what we've done so far? Are you still there?
Yes, we are.
Oh, fantastic. Good. Very good. Right. So there we go. So we kind of solved the problem. I think that solved the problem. Yeah, show your result in a diagram. Okay, so yeah, so what we want, I guess we could do this, couldn't we? So we could have our triangle here, and let's draw our incident ray coming off this one. That's sort of coming out and we need this one. That's going to be, our angle is 43. Okay, there we go. That's going to be 43.4 degrees. Okay. Now, and so what we can do here is if we then sort of rearrange this, so the argument of the inverse sine function of theta 4, that's got to be less than 1 or less than or equal to 1. So you can also say, if I draw a little sort of line here, so so for real values of theta 4, okay, what we need is n sine 75 degrees minus of sine theta 1 over is basically bigger than or equal to 1. Oops, other way around. Is less than or equal to 1. Okay, because otherwise, because the inverse sine function, the argument of that can't be, you know, so in other words, i.e., sine of theta 4 is less than or equal to 1. Okay, so if we do that, we've got a little expression to solve here. So what we can do is we've got 75 degrees minus inverse sine of sine theta 1 over n. Let's make that nice and big so you can all see it. Is less than or equal to, well, it's an inverse sine, right? Of one inequalities work in that case. So let's just rearrange this. So put that to the other side. So we've got 75 degrees minus inverse sine of 1 over n. Okay, is less than or equal to inverse sine of sine theta 1 over n. Bit of algebra today. Sine the rest. So we've got sine of 75 degrees minus inverse sine of 1 over n is greater than or equal to sine theta, there we are, over n. So we multiply by n and inverse sine that. So therefore, that's theta 1 is bigger than or equal to n inverse sine. Oops, wrong way around. So n, so we inverse sine, and we're going to multiply by n times the sine degrees minus inverse over n. There we go. I think it's the right number of brackets. So let's put the numbers in. So we've got inverse sine. We've got 1.4. We've got the sine of 75 degrees minus the inverse sine of 1 over n, what we said that was 45.6. So let's just do that again. So 1 over 1.4. There we go. And if you pop that into a calculator, guess what? You get exactly the same number. That's rather a nice result. So if you think about it, your input angles, so theta 1 has got to be basically between, I'll do this sort of the green ones here. The smallest it can be is 43.4 degrees. It's 43.4. So theta 1 must be bigger than 3.4 and less than or equal to 90 degrees for us to get something to emerge. I suppose I would probably be inclined of saying less than 90 degrees, because clearly you're not going to get any ray into this prism if it's actually at 90 degrees, but that's a bit pedantic. Okay, so yes, a nice problem here. So again, you look something that looks horrendous, but actually if you kind of think about the thing I've highlighted in red, that's how you might sort of go about this. You don't need to get algebraically admired. You just need to think about this sort of what the sign of that thing is, how big could it possibly be, what's that going to affect on the output. Okay, so there we go. We looked at geometry. We sort of defined our worlds. Getting some refresh problems here. Let's see if that's okay. There we go. I'm just going to go and restart my OneNote page. Just bear with me. There we go. Right. Okay. So, anyone got any questions on that one? In that case, we'll have a look at problem V, which is on capacitors. And that's probably going to be our last one. So our beast question, perhaps we can do that next time. Right. So let's go and have a look at V. And there we go. Right, here we go. So what do we got here? So it's a novel capacitor question here. Let's go have a little look. So we've got a capacitor of 1 farad that discharges through a device whose resistance varies linearly with a potential difference V. So that's an odd little thing, isn't it? So a resistance that varies with voltage. All right. And so we want to see how long it takes this capacitor to discharge. So this is a calculus question. And we're going to approach this in the same way that we derive any equations for capacitor decay. So firstly, let's just draw the circuit out. So here's a capacitor. And if you're new to what capacitors are, it's basically 2 metal plates separated by an insulator. And we can displace charge. We can sort of move charge. So we might have a positive charge on one plate and a negative charge on the other plate. All right, and they're not touching, so those charges can't sort of reapportion. All right, we have to do some work to make that happen. So here we go. That's the resistance R, and I'm going to have a voltmeter across this, and we've got some current flowing through this circuit. All right, and sort of as our capacitor discharges. So what can we write down? Well, we can write down using the definition of resistance. We can say that V equals IR. That's kind of handy. And we're told that R is AV plus B. So V is going to be I V plus B. And so therefore we have an expression for the current. So when you're looking at electrical circuits, basically trying to find the currents is kind of what you want to try and do. So V over AV plus B is to be our current. Let's call that equation number 1. Right, so how else can we write down our currents? Well, given it's a discharging capacitor, we know that the current that sort of comes off this is the rate of change of charge flow. And of course, the charge on our plates is decaying, so minus dq by dt. Right, we can use calculus notations. That's the gradients of the graph of q versus t. Right, minus that is going to be the current, because current's a positive quantity here. And we've also got our expression for capacitance. So can you tell us what that is? How does the charge relate to the voltage that we might have across my plates and also therefore across my battery? How does charge relate to voltage for a capacitor?
Yeah, Q equals C times V.
Fantastic. And yes, so C is going to be my capacitance in farads, the charge divided by the voltage. Brilliant. Right. So if we put those two things together, what we've got, remember Q we don't really care about, V we do, and I we do. So we end up with what we call a differential equation in terms of V and time, which is kind of what we want. So let's just put all of that together, shall we? So what we've got I is going to be minus C dV by dt. And therefore, if we put that together, call that equation 2. If we combine the two, so therefore, equating 1 and 2, what have we got? We've got minus C dV by equal to V over AV plus B. And right, for math fiends amongst you, we know how to do this. This is a separable differential equation. So what we do is we pretend they're fractions and we multiply things on both sides, get all the v's on one side and the times on the other, and then integrate. So let's have a look at this. So what do we got? Let's do that. So AV plus B over V dV, and that's going to be dt with a minus sign over C. All right, you think, gosh, that's cavalier. Well, we might think, well, mate, let's have a small finite difference, rearrange it and have a fraction, and then sort of shrink those things to become microscopic. I think that's perfectly fine. Anyway, that's how we do it. We rearrange the variables. Let's just make it a little bit simpler. So we've got A plus B over V, right, delta V, and we're going to sum up all of those. Let's start with some V naught, some sort of voltage to V. And we ought to probably call these little dummy variables because our end goal for our integration is V, but I think I'm just going to leave that in for the moment. I'm going to be a little cavalier. And if we sum up all our delta t's from 0 to t, that's just going to give us time. So we're in math land now. So if we integrate that, we've got AV, and then we put a log because we're integrating 1 over V. So what have we got? We've got AV plus B natural log of V. Okay, V naught to V. And we've got minus T over C. Okay, there we go. So if we and I hope you've already met that, but I'm using the fact of integration. So I'm summing up my 1 over v's. That gives you the natural log of the Planck constant. Okay, it's one of our fundamental calculus results. I'm going to assume this. So if we work this out, so what have I got? I've got AV plus B log V minus AV naught plus, and I've got a minus sign there, so minus B log V naught equals minus T over C. Let's change the signs around. So we've got A V naught minus V, and we've got plus B log V naught over V equals T over C. How do I know that? Well, I've got my difference of logs here. Okay, so this bit here, that's going to be log V naught minus log V. Okay, so what I want the discharge time. So that's what is it asking me for? So determine how long it takes for the capacitor to discharge to 1% of its initial value. So V naught is going to be this. And we can work out the constants from our input data. All right. So let's just rearrange this. So we've got an expression. So therefore, we've got T is going to be right. So we've got AC. All right. V naught minus V plus V log V naught over V. So there we are. There's our expression for time. But now we've got to figure out what the constants are. Right, we know the capacitance. So the capacitance is 1 farad, an enormous capacitor. Okay, we've got V naught. What's that one? V naught is 6 volts. And now we're told that so R equals 10 ohms when V equals 6 volts, and we've got 4 ohms when V is when V equals 0.06 volts. So remember what R equals A B. You can sort of solve that simultaneously. So we've got 10 equals 6A and plus B, and we've got 4. Whoops. We've got 4. Equals 0.06 A plus B. We do one for the other. How many equations we got? Let's call that 1 and 2. If we do 1 minus 2, we've got 6 equals 7.06. So 5.94 A is cancel. And therefore, A is going to be 6 over 5.94. In the units of our question, we can use maybe equation 1 to find B. So therefore, B is going to be what should we do? So we can use actually I'll probably use number 2 for this one. So B is going to be well, it doesn't really matter, to be honest. I'll use the top one. So 10 minus 6 times this one, so that's going to be 36 over 5.94. Yep. Okay, so there we are. And I think that gives you to 130 over 33. Let's just write that properly. And that's in ohms because that's what the resistance is. Okay, the other one's a strange unit of ohms per volt. So if we put all that together, what do we get? So I make that. Let's have a little look. So I think it's just the time we want. So if I just put that together, so therefore, just checking what we want. So up to 1% of its initial value. Right. So if you think about it, so what we want V over V naught. So V to be 0.01 of V naught, basically. So what we've got A times C. So 6 over 5.94 times 1. We've got 6.0. And we're taking away 0.01 times 6. And then if we add that to B, which is 30 over 33 times 1 times the logarithm of V naught. So that's going to be 6. Well, 6 divided by 0.01 times 6. So log of 1 over 0.01 or log of 100. All right, that's 100 here. And if you put that into a calculator, I make that 6 plus 18.14, which is 24 points. So there we go. A nice little capacitor question with a twist, which is where our resistance isn't a constant, but depends linearly on voltage. So we've got a slightly more interesting differential equation to solve, but otherwise very similar to capacitor decay that we normally meet. Okay, I think that is probably quite enough for today. Well done for sticking with it. And I think we've got another session next week. Is that right?
Yes.
Brilliant. And then do we have another session after half term, or is that it before round one?
No, we have the last one is after half term.
Right. Excellent. So there we go. I think if you've got any sort of questions in the chat that might be for that one, but otherwise we'll probably go to the 2019 paper for most of next week and the last one. All right. Thank you very much indeed, and have a good evening.